And let me share my screen on my iPad. All right, so right now, everybody should be able to see my notes that says chapter 15, sampling distribution. So for chapter 15, sampling distribution, what we're gonna do, we're kind of gonna transition over from having to randomly select one person to now randomly selecting n many people or n many objects. So you're saying instead of randomly sampling one person, we're gonna randomly sample n many people. So kind of think about it. The way it's gonna work, you're gonna have your population. So say this is your population. So we're gonna say our population consists of numbers. So we'll say 2, 5, 7, 8, 6, 4. So that's our population. So what the sampling distribution says that we're gonna make a new population or a new distribution with our old population. So say if we're taking a random sample of 2 numbers. So say we first randomly select these 2 numbers. So we randomly select 7 and 4. So what the sampling distribution says, once you randomly select from that population, we're going to take the average of those 2 numbers. So we're going to take the average of 7 and 4. So we're going to go 7 plus 4 is equal to 11. 11 divided by 2 is 5.5. So that's going to be our new data. So our new data is going to be 5.4. But then what's going to happen, we're going to now go back and we're going to randomly select a new set of numbers. So now we're going to randomly select 6 and 4. And we're going to get the average of those 2 numbers. So we'll go 7 plus 4 divided by 2. You get 5. So now our second data set will be 5. And what we're going to do, we're going to keep on going and going until you pretty much exhaust all of the different combination of how you can randomly select 2 people or 2 objects. And then we're going to make a new distribution with that. So to kind of illustrate that or demonstrate that a little bit better, I'm going to go over here to the simulation. And we're going to do sleep. There. Everybody can see like a right skew histogram right now? All right.
Yes.
Cool, thank you. All right. So if you look at this right skew histogram, it's telling us how many hours of sleep a person gets. So all the way from like 6, well, hopefully not 20 hours. So telling us like on pretty much how many hours of sleep a person gets. So what we want to do, we're going to randomly select from this population like I did with the other one. So I'm going to randomly select. For this one, how many people do we want to randomly select? Do we want to randomly select like 1, 2, 3, 20, 100? How many people do you want to get? Let's see the chat.
1.
Well, let's get something bigger than 1. Where is the chat? All right, so let's do 8. So I'm going to say 8 right here. And what I'm going to do, I'm going to hit draw sample. Right. So when I'm drawing a sample, this is a sample that I draw. So one person has 7.5, another person has 7.25, another person has 12, 6.75, 8, 8.5, and 7.5. So that's represented by this one below. So that's our sample. So once we get this sample, what we want to do, we just want to randomly, we just want to take the average of that sample. So when we take the average of the sample, if you look right here, it says 8.563. So that means we have this one data point. So what we're going to go ahead and do, we're going to go ahead and do another selection. So let's do a selection of 8 more people. All right. So now this is my new data set. So what we're going to do from that new data set, we're going to take the average of that new data set. So if you look right here, we have a data set which says that the average is 8.156. And that's our new data set. So this blue box right here, that's telling us that's the second new average that we got. Any question in regard to that so far? All right. So what this is meant to do, you're meant to do this like several times. So instead of me going one by one, I'm gonna tell this. I'm gonna tell the the applet. I'm gonna tell it to do this 100 times for me. So that way I don't have to manually do it 100 times. It will do that for me. So I'm gonna tell it to do this 100 times. So it's gonna draw me the distribution. All right. So if you look at it, it drew 8 sample, and then it got me this. So this is our new distribution. So if I look at the old distribution, and if I look at the new distribution, so the old distribution is the one to the left. What type of distribution would this one have? Is it skewed to the left, skewed to the right? What is it?
Skewed to the right.
Yeah, skewed to the right. If I look at this distribution, what type of shape does this one have?
Is it, symmetrical?
It's kind of symmetrical, but you can kind of see how it's a little bit skewed to the right, correct? Because like if it would have been symmetrical,
Yeah, it would have been.
this peak right here should have been more to the middle, correct? So it's a little bit skewed to the right. So the reason why it's still a little bit skewed to the right, the sample size of A wasn't big enough. What we're gonna do, we're gonna get a sample size bigger than 8. So what sample size do we want to go that's bigger than 8? And think big, but not too big. Well, let's do sample size of 50. And let's see what happened. All right. So here go my old distribution. So my old distribution is still skewed to the right. But I want to see now what happened to my new distribution. I want to see that the new distribution, is it still slightly skewed to the right? Or is it now a little bit more symmetrical? So let's move over and let's see. All right. So now that I'm looking at this, what does it kind of look like?
Symmetrical.
It's symmetrical now because since I increased the sample size, the increased sample size now is giving me something that's symmetrical. So for this one, if you take a big enough sample size from your original population, your new distribution that you're making will actually become symmetrical or approximately normal. All right. Everybody good so far with this? All right. So let's look at the old distribution. Let's look at the new distribution. So for the old distribution, what is my average? Or what is my mean? Well, if you look at it, it says right here 7.999. So let's go, I want to look at the new distribution. I want to see if the mean is still the same or it's completely different. So for my new distribution, is the mean kind of the same or is it completely different? So the old one was 7.999. The new one is 8.005. If you look at it, it's pretty much the same. It didn't change by that much. So if you look at it, it doesn't matter if you use the old population or the new population. The mean should still stay the same. So this mean will not change. But let's see what happened to the standard deviation. Because if you look at the old one, you can kind of see that the lowest number is somewhere probably like around 6. The highest number is at 20. So it has a pretty big spread. But if you look at the new one that we got, it's somewhere from 7.20 all the way to like 8.7. So it has a smaller spread. So let's see what standard deviation do we get in this one. So if you look at the standard deviation on top, it said SD, which is 1,501. Oh, sorry. Thinking 1,000. It's 1.501. So if you look where it says SD, you should be able to see that it says 1.501. But let's look at the new one. If you look at the new one, SD is 0.195. So it got smaller, and the reason it got smaller because you got a bigger sample size. So for this one, the bigger sample size we get from the population, the smaller our standard deviation should actually be getting. Because it's kind of saying, if you have a bigger sample size, based off of that bigger sample size, your standard deviation should be going down because it should be more accurate. If you have a smaller sample size, the standard deviation should be bigger because the standard deviation of a smaller data set should be smaller. All right. Everybody kind of good with that idea? Okay, so what I'm going to go ahead and do, we're going to go ahead and transition back to my notes. All right. So this is our new formula for mu and sigma, and this is kind of reflecting based on what we saw for the sampling distribution. Because if you remember for the sampling distribution, our mean didn't change, so that's why mu of x bar is equal to, yes, mu. But if you remember, standard deviation actually did change, and standard deviation changed based off of our sample size. So what we're going to do in order to get the new standard deviation of the sampling distribution, we're going to do standard deviation divided by square root of n. Cool. So, and also just know this is also called in the book standard error. So in the book, if you see something that says standard error, they're talking about this. Everybody good with the new formula for mu of x bar and sigma of x bar? Right. And don't worry about the z-score formula. For this one, we're going to let the calculator calculate the z-score formula for us. So don't worry about it.
What did it say there next to the Oh.
Standard error?
Hmm.
Yeah. All right. So right now we're gonna focus on the shape of the sampling distribution. So when we talk about the shape, we're talking about, is the data skewed to the left, skewed to the right, or is it symmetrical? So kind of, if you remember for the, what you call it, for the example or for the simulation that I was showing you about people's sleep, what was the shape of the original population? Well, if you remember the shape of the original population, the shape of the original population was skewed to the right, or right skew. Thinking on it. So it was right skew. But what was the shape of the new distribution that we got? So what was the shape of the new distribution that we got the second time around? We said it was what?
Symmetric.
Yeah, so it was symmetric, or other word that we could say is approximately normal. So what we were seeing, it was based off of the central limit theorem. So here's the central limit theorem. They also say CLT, yeah, for short. Ooh, stop sharing. All right. So it's called the central limit theorem. And the reason why we're seeing the data set become approximately normal is because of what the central limit theorem says. So what the central limit theorem says is that if we increase the sample size, or if we increase n, our distribution should become more approximately normal. So the kind of the rule of thumb is n has to be greater than or equal to 30. So if n, oops, don't want to use a highlighter. If n is greater than or equal to 30, we could say our data set is approximately normal. So that's what the central limit theorem said. It said if our n is greater than or equal to 30, we could say our distribution is approximately normal. And kind of you saw that when we did the distribution, especially when we did the distribution of 8, you kind of saw how it was still kind of a little bit right skew. But once we increased it to, I think, 50, you kind of saw that it started becoming more symmetrical. So that's what the central limit theorem is saying. It is saying if our distribution, or sorry, if our sample size is big enough, the new distribution of that sample size should be approximately normal. And usually the rule of thumb that we use to check is n has to be greater than or equal to 30. Any question in regard to that? All right. So one thing about the central limit theorem, you only apply the central limit theorem if the distribution is not normal. If I already know the distribution is normal, it doesn't matter what my sample size is. Pretty much the new distribution or the new shape of the new distribution will always be normal if my distribution start off as a normal distribution. Cool. So we only want to apply the central limit theorem when our distribution is not normal. Because if you look at this picture that I gave you, if you look at this, if it start normal, the new distribution or the distribution will still be normal. So if the original distribution start off at a normal distribution, it doesn't matter how big of a sample size we get or how small of a sample size we get, it would still be considered a normal distribution. You only really want to apply the central limit there for when your distribution is not normal. So for this one, we'll say we don't, oops. Apply the CLT since it is already normal. All right, so let's scroll on down. All right, so let's look at this distribution. Is this distribution normal?
Yes.
Well,
Well, no, because everything's the same. Like it's
yeah, if you look at it, there's no peak on this. It's essentially just all the same.
Yeah.
So this one is not normal. So we'll say not
normal.
normal. So for this one, we do want to apply the central limit there. So for this one, you do want to apply the central limit theorem because if you look at it, since it's uniform, that means it's not a normal distribution. So if you look at it, it starts off at not being normal, but what happened to it once we have a sample size of 50? What will we call this new distribution over here? Like what shape would it have?
Symmetric.
Symmetric. So now we'll say because of the central limit theorem, it is approximately normal. Cool. All right, and that's it for that second illustration. Any question in regard to that illustration?
Yes, we only said that it's not normal in the beginning because it was labeled uniform. Or
Well,
is there another way? Like we could tell.
well, if you look at the if you look at this one, how can you tell this is normal?
Oh, because it is symmetrical.
Because it's symmetrical. So if I would have given you that uniform, you could still look at this and go like, is that symmetrical? And you go like, no, it's not symmetrical, so that's why we say it's not normal.
Okay.
Okay, good question. All right, so let's go on to the third drawing.
Wait, so that's all we do for the the drawings or the diagrams that are there?
Yeah.
Okay. Like we don't need to add up numbers or nothing, right?
No.
Okay.
All right, let's look at this one. So is this first one, is that normal?
No.
No, so we'll say nah, normal. Need to apply the CLT. Cool. All right, so let's look at this one when n is equal to 50. Based off of this drawing, is it normal now?
Yes.
Yeah, so it is normal now. So since now it is normal, we could say this is approximately normal because of the central limit there.
Um,
But Also, if you kind of notice the reason why it will be approximately normal is because my n is 50. And if you look at that, 50 is greater than or equal to 30. Because in a little bit, we're going to be doing this for data set, but we're not going to have the distribution where you're pretty much just going to go based off our sample size. So pretty much based off our sample size, we're going to say if it's normal or if it's not normal. So you do kind of want to get the idea that if n is greater than or equal to 30, then we could say is approximately normal. And I forgot the normal over here. All right. So let's go ahead and let's do some math. All right. So this is just pretty much a summary. So it's saying it doesn't matter if it's right skew or uniform or U shape or left skew. If n is greater than or equal to 30, our new distribution should look symmetrical or normal. So pretty much that's the idea of what we were doing for the last like 3 illustrations. It was just saying it doesn't matter the shape of the original population, as long as we're sampling at sample size greater than or equal to 30, the new distribution should look approximately normal. So that's like the big idea that hopefully you should have gotten based off of those 3 illustrations. All right. Any question in regard to that? All right. So let's go ahead and do some math. So right here, we're going to do describe the sampling distribution of the sample mean. So whenever I say describe the sampling distribution of the sample mean, whenever we want to describe it, we kind of want to give 3 things. We want to give the mu of x bar, the sigma x bar, but we also want to give the shape of the distribution. So we don't want to give the shape of the original distribution. We want to give the shape of the new distribution depending on how big of a sample size we're getting. So let me just put this right now. So we want to find what mu of x bar is equal to, which this is just equal to mu. We want to find what sigma of x bar is equal to, which this is just equal to sigma divided by square root of n. And we also want to say, is the distribution normal? Is the distribution going to be not normal? Or is the distribution going to be approximately normal? And usually the reason why we will say approximately normal is if we had to use the central limit theorem. So if we use the central limit theorem to say something is normal, we're going to say it's approximately normal. All right. So let's go ahead and let's read the problem. So it says describe the sampling distribution of the sample mean for mu is equal to 20 and sigma is equal to 12 for a sample size of 9 if the sample come from a normal distribution. So the first thing I want to go ahead and do, we're going to find what mu of x bar is equal to. So mu of x bar is equal to mu. So what do they tell us mu is equal to in this problem?
20.
Yeah, 20. So we'll put 20 there. And that's it. So that's your mu of x bar. Mu of x bar is equal to 20. Any question about mu of x bar? All right, let's do sigma of x bar. So for sigma of x bar is equal to sigma divided by square root of n. What's my sigma equal to in this case?
12.
Yeah, 12, thank you. And what's my n in this case scenario?
9.
All right, perfect. So if you do 12 divided by square root of 9, that's 12 divided by 3, which 12 divided by 3 is 4. All right. And that's your answer for sigma of x bar. So sigma of x bar will equal to 4. Any question I got sigma x bar equal to 4? Okay, so up next, we're going to try to see if the data set is normal, not normal, or if it's approximately normal. So you always want to check to see first if it's normal. If it's normal, the problem or the original problem should tell you the distribution is normal. For this problem, do they tell us the distribution was normal?
Yes.
Yeah, good. If you look right here, they tell us a normal distribution. So since they tell us it's a normal distribution, we say it is normal. And that's it for A. So for A, we're going to say mu of x bar is equal to 20, sigma of x bar is equal to 4, and this is a normal distribution. And that's it for part A. Any question for part A? All right, let's do part B. All right, so for part B, it says describe the sampling distribution of the sample mean for mu is equal to 20 and sigma is equal to 12 for a sample size of 100 if the sample come from a skewed distribution. All right, so let's do mu of x bar. So mu of x bar is equal to mu, and mu is equal to what?
20.
Yeah, 20. Now let's do sigma of x bar. So sigma of x bar is equal to sigma divided by square root of n. Sigma is equal to 12, which is the same thing as part A. But what is my sample size equal to?
100.
100. So if I do 12 divided by square root of 100, you actually get 1.2. All right. Everybody good? I got 1.2. Okay, lastly, what we want to do, we want to check to see if the distribution is normal, not normal, or approximately normal. So to check to see if it's normal, the problem has to tell you is normal. So what type of distribution does the problem tell us this one has?
Skewed.
Yeah, so they tell us it's skewed. So since they're telling us it's skewed, they're telling us it's not normal. So it doesn't start off as a normal distribution. So now what we want to do, we want to see if it should be considered normal, or sorry, approximately normal, or if we should say it's not normal. So if it's not normal, that means it didn't pass the central limit theorem. If it's approximately normal, that means it does pass the central limit theorem. So to see if it passed or not passed the central limit theorem, all you have to do is check to see if n is greater than or equal to 30. So in this case, since n is 100,
Approximately.
n is 100, so 100 is greater than or equal to 30. So that's actually a true statement. So that means we have a approximately normal distribution, and that's because of the central limit theorem. And that's it for B. All right. Everybody good for B? All right. So let's do C. So C says, what do you notice? So I'm going to change that a little bit. So we went from an n that would equal to 9, and then we upgraded to an n that's equal to 100. So what we're going to do, we're going to say what happened to mu of x, and we're also going to say what happened to sigma of x bar. So we just want to say, did it stay the same? Did it decrease? Or did it increase? Same thing for sigma of x bar. We're going to say, did it stay the same? Did it decrease? or did it increase? So let's do mu of x bar. So for mu of x bar, if you look at it for A, it was 20. If you look at it for B, it was still 20. So for mu of x bar, did it stay the same? Did it decrease or did it increase?
Same.
Stayed the same. So we're gonna say stay the same. What about for sigma of x bar? Did it stay the same? Because it originally started off at 4 and then it changed to 1.2. So did it stay the same, decrease, or increase?
It decreased.
It decreased. So that kind of goes to show you how the bigger the sample size you have, the more accurate it should be. So if it's more accurate, that means standard deviation of x bar should start decreasing or get smaller. If it actually increased, that means you have a smaller sample size. All right, but that's it for C. Any question for C?
No.
So what I want you to do, I want you to try out this problem. So for this one, describe the sampling distribution. So just do what we did for the last one. So just fill these out. So you take a minute and just do this. Once you get the answer, you just enter it into the chat. For that way I can let you know if you did it correct or if you need a little bit of work. Okay, so let me do something because apparently it stopped sharing. So So what do we get for mu of x bar? Oh, mu is equal to 30. Perfect. What about for sigma of x bar? What do we get? Perfect. All right. And for this one, what do we get for the distribution? The normal, non-normal, or approximately normal? Not normal. Good. Yeah, okay, if you look at the prompt, nowhere does it say that the distribution is normal or anything like that. So we're gonna just assume it's not normal. And if you look at the sample size of 20 is not bigger than or equal to 30. So that's why we're gonna say that this is not normal because the problem doesn't tell us it's a normal distribution, but also because we can't apply the central limit theorem because for this one, the sample size isn't big enough. All right, but that's it for that problem. Any question for that problem? Okay, so let's go ahead and let's do this next problem. So right now we're gonna do example of sampling distribution. So for this one, we're going to take what we have learned about describing a sample distribution, and we're now going to apply it into how to find the probability. So for this one, to find the probability shouldn't be that bad, because if you still remember how to find the probability of a normal distribution, we're still going to be using that knowledge. The only thing is we have to just adjust the standard deviation. Okay, so if you look at this problem, it tells us mu is equal to 70, sigma is equal to 20, and n is equal to 16. And if you look right here, they tell us the distribution is normal. So we already know the distribution is normal, so there's no need to check the central limit there. So that means if we already know it's a normal distribution, that means we can go ahead and find the probability for this one. So let's go ahead and find the probability for this one. So for this one, we're gonna get, so we wanna find what mu of x bar is equal to. We're gonna find what sigma of x bar is equal to. So for this one, what's mu of x bar equal to?
70.
Yeah, 70. So you put 70. And then if you look at sigma of x bar, you'll get that by doing 20 divided by square root of
16.
16, which is equal to 20 divided by 4, which is equal to 5.
Right.
Everybody so far good with mu of x bar and sigma of x bar? All right. So let's go ahead and draw this out. So the middle should be mu of x bar, so that'd be 70. If you look at it, we want to find the probability that x bar is greater than 67. So 67 is slightly over here. And which side do I want to shade? Do I want to shade the left side, or would I want to shade the right side? So left or right?
Left.
Left.
Well, if you look at this inequality, which side is it pointing to? Is it pointing to the left or pointing to the right?
Or the right.
Right.
The right. So you want to shade the right. There you go. All right. Everybody good so far on this? Okay. So up next we're gonna go ahead and do, we're gonna go ahead and just figure out how will we enter this for in the calculator. So in the calculator, it's gonna ask you for 4 things. So it's gonna ask you for mu. It's gonna ask you for sigma. It's gonna ask you for the lower bound. And it's gonna ask you for the upper bound. So for mu, we said 70, so you put 70. For sigma, you don't want to put this sigma. You want to put this new sigma. You want to put what sigma of x bar is equal to, so we're going to put 5. If you look at the lower bound is the lowest value that I have shaded.
67.
So that's 67. And for the upper bound, you want to put the highest value that's shaded. So if you look at it, since you keep on going and going to the right-hand side, so you can be going to infinity. If you're using a TI 83 or 84, you want to say 10 to the 10 power, because your calculator doesn't have an infinity option. All right. Everybody good so far? I got mu is equal to 70, sigma is equal to 5, lower bound is equal to 67, upper bound is 10 to the 10 power or infinity.
Yes.
Perfect. All right. So what we're gonna go ahead and do, we're gonna go ahead and we're gonna transition over to class calc. So if you remember, you first hit the stats button, you then hit distribution, and then you find normal distribution. So remember, hit stats, hit the stats button, hit distribution, and then do normal distribution. And if you look at the normal distribution, I say, give me mu and give me sigma. So we'll say 70 is mu, sigma is 5. And we'll close that. So far, everybody good with normal distribution 70, comma 5?
Are we in graphing, right? Or no?
Yeah, you're in graphing. Pretty much anytime you're using class calc, you should always be in graphing.
Okay.
So then what you want to go ahead and do, you want to hit the CDF button. So the CDF button, the left one is the lower bound, the right one is the upper bound. So for the lower bound, we said it was 67. The upper bound is just positive infinity. And if you look at that, it gives us the probability. So we'll say probability that X bar is greater than 67 is equal to 0.7257. And that's your final answer. So if you kind of look at it, it's pretty much the same that we did before. The only thing different is that you have to adjust the standard deviation. You can't just push the standard deviation. You have to do standard deviation divided by square root of n. Because if you put the wrong standard deviation, it will give you the wrong answer. All right, but that's it for class calc. Any question in regard to class calc? Okay, so for the people who do have a TI-83 or 84, I'll show you right now how to do it. So we'll say, oops.
Do we work on the next one?
Yeah, if you want, you can work on the next one, or you can just chill right now. All right, so for people who have the TI-83 or 84, what you want to go ahead and do, you want to hit the second button. So you want to hit the blue button. And then you want to go where it says VARS. So in case I went too fast for you. So you go to second and go VARS. So if you look at it, you should be in this screen where it says normal PDF, normal CDF. Well, we're going to say normal CDF. So for the lower will be your lower bound. So that's 67. Your upper bound will be infinity, but remember, you don't have infinity, so you put 10. And then if you look at this button right above the division sign, that's the one you want to use. That it looks like an arrow pointing up. And then you put 10 again. And then go to mu, where mu is equal to 70. And then sigma is equal to, what is sigma equal to? 5. Then you go to paste, and then you just hit that. And you should get exactly the same answer that I did from before. All right. Any question in regard to how to deal with a TI-83 or 84? All right, so we're gonna go back to my notes, and that way we can work on this part B.
Would the decimal like 0.7257, that would be our final answer? Okay.
Yeah. Yeah, if you look at the notes right now, yeah, this will be our final answer. So once you find the probability, you're done. All right, so let's do part B. So for part B, here, let me go ahead and draw this again. Oops. So we have 70 over here. Then if you look at it, we want 72, which is over here. If you look at the arrow, it's pointing to the left-hand side, so you say the left-hand side. All right. So up there, we have to fill out mu and sigma, but mu and sigma is gonna be the same. It's still gonna be 70 for mu, and for sigma, it's still gonna be 5. So all we have to do is find the lower bound and the upper bound. So for the lower bound, what is our lower bound?
Infinity.
Well, what type of infinity though?
Negative infinity.
Negative infinity. Sorry about that. Yeah, so you want to do negative infinity. If you're using the TI-83, you want to say negative 10 to the 10 power. For my upper bound will be the upper value. So the highest value that I have shaded, if you look at it, is a 72. So you put 72. Thanks, Victor. All right. So we get upper bound is 72. We get lower bound is negative infinity, which is negative 10 to the 10 power. So now what I'm going to go ahead and do, just go to class calc. And we're going to do this again. So the cool thing about class calc, like you don't have to re-enter the normal distribution. You can just press right here where it says clear. And then you can just re-enter the lower bound and the upper bound. So the only thing I have to do is put the upper bound, which is 72. And we're done. So we'll say probability that X bar is less than 72 is equal to 0.6554.
4.
Any question for B? All right, so let's do C together. Here, let me share my screen for that way you can see what am I doing. All right, so far I have 70 is in the middle because that's my average, and then we have 77, which is on the right side 70 because 77 is bigger than 70. So if you look at the arrow is pointing to the right, so that means we want it to be bigger than 77. So you shade the right hand side. Everybody good so far with that drawing? All right, so if you look at the lower bound is always the lowest value that you shaded. So here's the lowest part that I shaded. So that's my lower bound. So that means my lower bound would be 77. For my upper bound, the highest value that I shaded, if you look at my upper bound, there is no real true cutoff because you keep on going to the right-hand side. So that's why you want to put infinity there. Or if you have a TI-83 or 84, you put 10 to the 10 power. Any questions so far with those inputs? Okay, so this time around, I'm gonna go ahead, I'm gonna do this with the TI-83, well, technically TI-84, for that way for people who have the TI-83 or 84. All right, so you just wanna go second, you wanna go to bars, you wanna click right here where it says normal distribution. So if you look at my lower bound, I want it to be 77, so you change that from 67 to 77. My upper bound is actually 10 to the 10 power, so leave it as is. My mu, my sigma should stay the same, so let me hit paste, press enter, and we get 0.0808. So we'll say probability that X bar is greater than 77 is equal to 0.0808. All right, but that's it in regard to that third problem. Any question for that third problem? All right, so for the fourth problem, what I'm gonna let you do, I'm gonna let you do it by yourself. I'm gonna put up a poll for that way you can answer which of the answer it should be. So if you haven't done D already, do D. And then just answer the poll with which answer you think it should be.
Gosh.
All right, so here are your options.
Do we just put it in the chat?
No, I'm gonna put the poll up right now. So let me launch the poll. Question. Launch. Go. So, yeah, so you have to put it on the poll which one you think should be the answer. All right, so let's stop the poll. Let me share the poll. All right, so if you look at for the people who did participate, you chose B. Oh, and B is the correct answer. Perfect. All right. So let's stop share. All right. So up next, we're gonna go ahead and do a word problem, so that way you can apply it. So for this one, it says suppose a elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assume male weight follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. All right, so for this one, it kind of makes sense why they're using male weight versus female weight, because male you tend to weigh more than female. So it kind of makes sense why do you want to just focus on how much do male weigh versus female, because if they use female, they might make an elevator that can like withstand a male. All right, so let's look at the information that they give us. So let's find mu, let's find sigma, and let's see if they tell us the distribution is normal. So for this one, what's our mu? Well, if you look at mu,
182.
yeah, perfect, Imani. So 182.9. Thank you, Victor. What about our sigma? What's our sigma?
40.8.
Yeah, 40.8. And for this one, do they tell us the distribution is normal?
Yes.
Yes. Cool. All right, so we're gonna go ahead and do this problem. So for part A, it says for this problem, do we need to apply the central limit theorem? So do I need to apply the central limit theorem? No. Because the distribution is already normal. Yeah, good. Good, Victor. Yeah, since it's already normal, there's no need to apply the central limit theorem. All right, so let's do part A. Oh, sorry, part B. So for part B, it says find the probability that one randomly selected male has a weight greater than 156.25 pounds. So for this one, how many male are they randomly selecting? Are you sure about that, Victor? Well, for part B,
One.
yeah, if you look at it, it says find the probability that one randomly selected male. So for this one, n is equal to 1. So let's go ahead and draw this out. So we'll say the middle should be 182.9. We want it to be 156.25. If you look at it, it says greater than, you say the right side. Everybody good with my drawing so far? Okay, so let's go ahead and see how we're going to enter this into either Class Calc or your TI 83 or 84. For this one, what should be my mean? What should I put for mu?
The 182.
Yeah, 182, thank you. So we put 182.9. All right, what should I put for sigma? So what's my sigma guy? Yeah, 40.8. For this one, since we're doing for a sample size of 1, my sigma is my sigma. It doesn't change. All right, let's do stop share. Let's do share. Yeah, so you get sigma 40.8. For this one, what will be my lower bound? Cool, thanks, Victor. So 156.25. And then my upper bound will be the upper value, so positive infinity. Thank you, Victor. So we'll say positive infinity. So you say 10 to the 10 power. All right. Everybody good so far on what we're entering into Class Calc? Okay, so let me switch over to Class Calc. So that way you can kind of see me entering this information. So for Class Calc, we're going to put mu is 182.9. Sigma is 40.8. And then for my lower bound, we put 156.25. For my upper bound, it's just infinity, so just leave it blank. So if you look at our answer, we get 0.7432. So we get, let me box it. So we get 0.7432. And that's it for part B. Any question in regard to part B? All right, so let's do part C. So for part C, it says, assuming a worst case scenario in which the passenger are all male, what are the chances that the elevator is overloaded? Find the probability that a sample of 16 male have a mean weight greater than 156.25. So pretty much this drawing is the same. But what's my n now? So n is what? Well, if you look at it, it says 16 male, so it's 16 now. So now we have to adjust our sigma. But the lower bound and the upper bound will remain the same. So we'll say lower bound is 156.25. Upper bound is positive infinity or 10 to the 10 power. Mu will be 182.9. Sigma in this case, you're going to do 40.8, but you have to divide this by square root of 16. Any question why we're doing 40.8 divided by square root of 16? Cool. All right, so if you do 40.8 divided by square root of 16, it actually ends up to be 10.2. Any question where the 10.2 come from? Okay, so let's go over to class calc. So the only thing I have to do, you change the 40.8 into a 10.2. And if you look at it, we get 0.9955. So you get 0.9955. Everybody go with that? All right, so then part D asks which part has a bigger probability, part B or part C? So which one has a bigger probability, part B or part C?
B.
Are you sure about that? Well, part B has 0.7432. Part C has 0.9955. So it should be part C. All right, and that's it for that question. Any question in regard to this problem? Okay, so that's it for the lecture note. But I do want to show you where you're going to be taking the quiz. So let me show you my screen. So that way you can see where you're going to take the quiz. All right, so for the quiz, all you have to do is go to Math 132. And then what you want to do is go to Contents. And if you look right over here, it's going to be right here. The quiz is going to be called Quiz Chapter 14. So for Quiz Chapter 14, let's see, you'll have 30 minutes to do 5 questions. And for this one, once you open it, you have to take it. And it's going to be due all the way till next Tuesday. So it should be open on Friday. So you're going to have the weekend or Monday or Tuesday to do it, but you're gonna have all the way till Tuesday to be able to do this quiz. Any question in regard to the quiz? All right, so that's pretty much it for me for today. So remember, if you do have any questions about anything,